So we're about to define some new adjectives that can be applied to a function mapping x to y. So assuming f maps x to y, here are some new adjectives that could possibly describe f or not. Here are their definitions. So here's the first adjective, injective. We say f is injective if and only if for all x and y in the domain of f, but I actually don't need to say domain of f. I can say x, big X, since I have introduced, this is part of why we write this notation, is that we have a nice short name for the domain of f, so we don't have to write this annoying symbol. For all x, y in the domain of f, we have that if f of x equals f of y, which these are things I can talk about since x and y are in the domain of f, I can evaluate f at x or y, then we have x equals y. So normally, of course, if you have x equals y and x and y are in the domain of f, then you would have this. So normally this arrow going down this way, this implication, is immediate. That's just from axiom 2, right? If two things, or I guess it's theorem 4, right? If two things are equal, then any object that has one of them is equal to the same object with the one thing replaced by something it's equal to. So this one is sort of immediate by just how equality works. If x is the same as y, then f of x is the same as f of y. But it's the other direction that gives you injectivity, what we call injectivity, that this equality can give you this equality. So not all functions have this feature. When they have this feature, the ones that do have this feature are described as injective. And notice there's a for all here, for all x, y in the domain. So when you're proving injectivity, you do a universal generalization kind of argument. Consider any x, y in the domain, assume fx equals fy, and then try to prove x equals y. And if you are using injectivity, it would be more of a universal instantiation kind of thing. I think it helps to also think about, instead of this implication, the way it's written, think about the contrapositive of it, which is equivalent. Contrapositive implication is equivalent to it. X not equal to y implies fx not equal to fy, right? That's another way of writing the same implication, since I can just take the contrapositive and get an equivalent statement. So this is saying whenever two things are in the domain of x, whenever two things are in the domain of f, if they are two different things, then their outputs are different. The corresponding output will be different. So let's think about this in terms of the picture. And there's more to definition 57, but I'm going to introduce the ideas one at a time. So let's think about this in terms of the picture. Actually, first let's think about it in terms of a set of pairs with no picture. So let's define capital X and capital Y, just like in the last video, and assume that these x, little x, y, z, a, b are all distinct. And let's say f is this. Then would you say that f is a function? What do you think? So my answer is yes, it's a function. And definitely it maps x to, well, it actually doesn't. It maps this to y, right? Since z is not part of the domain. Question, is this injective? So to check that it's injective, you need to verify that whenever two things are different, two inputs are different, the outputs also end up being different. So with this, x and y are different, right? We have x is not equal to y. That's because I'm assuming they're all distinct. Everything's distinct. But look at this. fx is a, right? Do you know how I formally know that, by the way? fx is a. It's essence of evaluation. So fx equals a is the same as saying, maybe I'll look at it this way. fx equals a is the same as saying that the pair x comma a is in f. And you see the pair x comma a is an element of f. So fx equals a. Similarly, fy equals a, right? So we have fx equals fy. This situation where x is not equal to y, and yet fx equals fy, this is what non-injectivity looks like. So here f is not injective because of this situation. And if you just think about what it is we had to do to check that f is not injective, is we had to find some pairs in f with the same second position but different first positions. Right? Find same second position, different first positions. So does that sound familiar to you? Hopefully that reminds you a lot of how to check whether something is a function or not. Hopefully it reminds you of the definition of function. It's just flipped around. When you're checking whether f is a function or not, you would look for a different sort of thing. You would try to make sure that whenever the first positions are the same, the second positions are different. But for injectivity, it's the other way around. You check for whether when the second positions are the same, the first positions are different. This is a more convenient way to state the condition of injectivity using function evaluation notation. But you can state it in terms of pairs and pair membership, just like we did for the definition of being a function. So what I'm referring to by definition of being a function is definition 48, this big for all x, y, z condition. It says, whenever two pairs are in f with the same first position, the second positions must also be the same. Now, what we're looking at here right now is the definition of injectivity, which on the face of it looks like something quite different, since it uses this evaluation notation. And it's defined this way because this is a convenient way to think about it and use it. But look to Theorem 58 if you just want to see how it looks similar to functionhood, but with the pairs flipped. So you see theorem, not definition, but theorem, f, assuming f is a function, f is injective if and only if this is true. Whenever two pairs are in f with the same second position, the first positions also match. Okay, so I'm not going to prove this theorem in lecture. I'm hoping that you're going to study that as part of your reading. But hopefully you're seeing that it's a plausible result considering what we had to think about to check for non-injectivity here. In practice, when you're working with the idea of injectivity, like you're trying to prove a function is injective or not, in almost all cases, I would suggest using this directly rather than using this. This is kind of here just to appreciate how similar it looks to our definition of being a function. So this theorem is here for appreciation, to be appreciated, not so much to be used. This is really more useful. Okay, let's look at some pictures and just get down what is the picture of being or not being injective. Okay, here was our example from earlier where we said yes, so this was our picture, this is it written out as a set of pairs, and yes, this is definitely true that it maps, f maps x to y. Is this injective? So what do you think? And here's my answer. Absolutely not. Not injective. So hopefully that's what you thought. And here's a typical picture of not being injective. Actually, it doesn't have to be three things coming into the same position. So let's just modify the example a little bit just to show that it's enough for two things not to be coming in. So let's say z is actually going to be here. And I would still say f maps x to y, and I would still say this is not injective. So this here is a picture of not being injective. Non-injectivity of f is depicted right here, and this right here, this is what it will always look like. Okay, so it's just like the mirror imaged version of what it looks like to not be a function. And you should pay attention to this, the for all aspect in the definition. Let me go to the one I wrote here. Where'd that go? Here. Pay attention to this for all aspect. So it's saying injectivity requires that whenever you have two distinct, let me write it just this one way rather than in two different ways. Injectivity requires that whenever you have two distinct inputs like this, that the outputs are also distinct for any pair of inputs. So if there's even a single violation of this, then your function is not injective. For a function to be injective is hard, in some sense, because you have to satisfy this for all, this universal. So here, this one bad apple, A, ruins it for everyone. So it could be that maybe y consists of many points, all of which have either no or just one green arrow going to them, but then just because A here is greedy and hogging these two green arrows, that ruins it for everyone, and this function is not injective. Okay, let's revisit this example. In this example, we also have f being a subset of the Cartesian product x product y. But we decided it was false that f maps x to y, but that was just because the domain wasn't all of x. So let me just modify this to make it true, actually. And I'll write down the actual domain of f here. It consists of x and z. So there. Now this is true. This mapping statement is true. Now, it doesn't really matter anymore whether we draw y in this picture or not. I'm going to keep it just because I have been, so far, drawing pictures of subsets of capital X product capital Y. So I'm just going to keep it, but it doesn't really affect my picture of what f is. Right? F just doesn't even involve little y in any way. Anyway, here's my question for you then. Is this f injective? What do you think? And my answer is yes, it is injective, and hopefully that's what you thought as well. So it is not only a function mapping this set to that set, but it is an injective one. Or sometimes we use injective as an adverb, and we say f maps this set to this set injectively. Sometimes we also use an alternative terminology, which is one-to-one. Sometimes you will hear this. F is a one-to-one function. So to be a function means every input has this output associated with it, clear decision about what the output should be for any given input, but also no collisions. So that's injectivity. So here we have collisions. This is not injective. X and Y, yeah, they have clear output, A, but there's a collision. They have the same output. A one-to-one or an injective function, no collisions. So to every input, we associate only one output, that's functionhood, but also for every output, there's a unique associated input, that's injectivity. Alright, so that was the first part of definition 57, and in the next video I'll introduce the next part of definition 57, which is another adjective. It's surjectivity, and I'll also introduce the third one, which is a combination of the first two.